Hello world, it's Craig. I get a fair number of questions about programming. Now 95% of the programming I do nowadays is in assembly for the 8085 and earlier processors. If the question isn't in this little niche, I just tell whomever that they're asking the wrong guy. For those people that I can help, sometimes it's a person trying to learn assembly language for the first time, and I'm all on board with that. And other times it's somebody that was good at assembly 50 years ago and they're getting frustrated trying to pick it back up. Now believe me, I can really sympathize with that. To help us all out, maybe even future me, I think I'll occasionally do a video on the more commonly asked questions I get on assembly programming. So in this video, let's look at some assembly language snippets to convert from hexadecimal to ASCII. So for example, we want to take a hexadecimal value in the A register and send it to the console or a printer or a smart display or some other output device that only understands the ASCII character set. Remember that one byte will contain two hexadecimal characters. So for example, if the byte is 3E and we want to send this to the console, we need to take the 3 in the high nibble, convert it to ASCII 33, and send it out. And then we take the E, convert it to ASCII as 45, and send it out. So in these examples, we're going to do the conversion one nibble at a time. And the basics of the conversion are just this. If the input is a number from 0 through 9, all we need to do is add 30 to make it the ASCII character, which go from 30 through 39. If the input is A through F, then we just need to add 37 to make it the ASCII character from A through F. We can look at three different ways of doing this. There's my favorite way, and then two of Intel's ways. The first Intel example takes one less byte than my code does, but it mostly seems like an excuse to use the DAA instruction. Then the second Intel example technically takes even one less byte than their DAA method, but it requires a lookup table. Now all of these code snippets are down in the description. When we need to convert from a hexadecimal value to ASCII, life would be so much easier if the letters came right after the numbers in ASCII. But there's these 7 other characters that are between them, which means that we have to treat the hex input value differently if it's a digit 0 through 9 than it is if it's a letter A through F. So the conditions are the same for these first two examples. The input value is in the accumulator, the result is left in the accumulator, and the utility uses the return instruction when the conversion is done to get back to wherever it was called. So given the input value of the accumulator for the numbers 0 to 9, all we have to do is add the 30 hex to the input value, and it is the ASCII character. In my code, I do that by just adding the ASCII value of 0 to the input and let the assembler figure out what the value actually is. If I added 30 and the result is ASCII 9 or less, meaning it's less than 3A, then the conversion is done and the utility just returns. If the addition caused the value to be larger than 9, then the utility needs to bump it up again to skip past those other 7 characters, and then the conversion is done and it can return. So this took 10 bytes of code, but I made my utility so the bulk of the code is recycled if I want to convert the high nibble or the low nibble. So if we call the utility up here at 2 ASCII high, first it rotates the top nibble down, and then it falls into the 2 ASCII low code that we just looked at. Now let's look to see how Intel does this in their monitors for platforms that are, the 8085, 8080 platforms. Let's look for the monitor for the Intel's 80p system or the System 10 or the System 20, for example. And these were all 8080 systems. The top nibble still needs to be cleared, so that line of code is the same as mine. Then for them, the first conversion instruction is to add 90 to the input value. Since the input was 0 to F, the accumulator is now going to have the value ranging from 90 through 9F. Now we're going to go through the rest of the code twice. Once if the input value is 0 through 9, and the second time if it's A through F. It just gets too confusing if we try to think about both at the same time or switch back and forth. So first, the 0 through 9 case. Now here's the first time they played the DAA card, which is the decimal accumulator adjust. The accumulator value is from 90 to 99, and the carry flag is not set from the 90 addition. Since both nibbles are 9 or less, the DAA instruction does nothing. The accumulator will still have 9 as the high nibble and the input value is the low nibble, and the carry flag will not be set. So in this case, the DAA doesn't do anything. Their next instruction is to add 40 hex, but with the carry. Notice when they added 90, it was without the carry. This time they add 40 with the carry. But for the 0 through 9 case, it doesn't matter anyway because the carry wasn't set. Adding 40 will leave the accumulator with a value from D0 through D9. There was no carry output, so the carry flag isn't set. Now they play the DAA card again. Now DAA will have no effect on the low nibble or the auxiliary carry, but 6 will be added to the high nibble. It was D, so now it will be EF0123. The accumulator contents are 30 through 39, which are the ASCII values for the numbers 0 through 9. The conversion is complete. The utility can return with the ASCII value in the accumulator. Now let's back up and do the A through F case. After the 9-0 addition, the accumulator contained 9A through 9F, and the carry flag was cleared. Since the low nibble is above 9, the DAA instruction is going to add 6 to the low nibble. If it started out as A, it'll be A, B, C, D, E, F, 0. If it started out as B, it'll be 1, and so forth on up to if it started out as a F, it'll now be 5. All of these cause the low nibble to roll over and create a half carry, which then increments the high nibble. That was 9, so the high nibble will increment up to A. The DAA has to fix that to keep it BCD, so it will add 6 to the high nibble. It was A, so adding 6 goes BCD, E, F, 0. The accumulator is now 0, 0 if the original input was A, and on up to 0, 5 if the original input was F. But unlike the 0 to 9 case, the carry is going to be set because the high nibble rolled over. Now when it does the add with carry instruction, adding 40 to 0 something becomes 4 something, and then add the carry, and that becomes 4 something plus 1. So if the starting value was A and the accumulator was 0, 0 before the addition, after the addition it's going to be 4, 0 plus the carry, which makes it 4, 1. If it started out as 0, 5, it's going to be 4, 6 when all is done. And these are the ASCII values for the letters A through F, so the conversion is actually done at this point. We know the DAA isn't going to change the accumulator since both nibbles are 9 or less. And now DAA will clear the flag, but that's about all it's going to do. The conversion is complete, utility can return. It's a bit interesting that the first DAA only has an effect in the A through F case, and the second DAA only has an effect in the 0 to 9 case. So as you can see, where my version took 10 bytes to do the conversion, the Intel code only takes 9 bytes. And I will admit, when I was desperately needed that 1 byte back, trying to get something to fit in a page, for example, I've been known to use Intel's version no matter how much it obfuscates the logic. But generally, I prefer to use my code since I think it's much more readable. Last example is another of Intel's resident monitors. This time it's from the STK85 system. Now this isn't exactly the same setup because it gets the input hex value and leaves the ASCII value in the C register rather than the accumulator. This method requires a lookup table. So somewhere in ROM is this table that has all the hexadecimal values from 0 through F stored as data bytes. The data bytes are just the ASCII values, 30 for 0, up to 39 for 9, and then it skips up to 41 for A, and up to 46 for F. So now let's look at the conversion utility. They do a double register load into HL, the starting address of that lookup table. They 0B, and the input value is in C, so now the BC register pair is something from 0000 up through 000F. Next step is the double register add of the input value in BC with the lookup table HL, and the result is being put back into HL. So this offsets the HL memory pointer up the table by whatever the input value was. So input is 0 and HL is pointing to the first entry in the table. Input at F and HL is now 16 bytes higher, pointing to the last entry in the table. If you forget to clear the high nibble before calling the utility, now the HL pointer is pointing somewhere in the great beyond. Since HL is just the memory pointer, the last step is to replace the original hexadecimal value in C with the ASCII equivalent using the move from memory instruction, move C from M. And then it just does a return. Now this method only took 8 instructions, so technically 1 less than the DAA method, which is great if it weren't for the 16 additional bytes needed for the lookup table. All totaled, it took 24 bytes or 2.5 times larger than using the DAA method. They did save the accumulator, but pushing and popping the accumulator would have only taken 2 more bytes. So I can't really see why they use this method other than it to serve as an example of lookup tables and the double register add and that kind of thing. If other places in the resident monitor needed to use that lookup table, then it would make more sense if that table already had to be there. But I didn't see in the STK85 monitor where that table was utilized by anywhere else. So maybe somebody else has some insight on this. All right, well, let me know if these sorts of videos are even worthwhile. Let me know your preference for this conversion, how you do it, and how you feel about that gratuitous use of the DAA instruction. And if you know of the reasoning behind them putting the lookup table in the SDK85. Okay, thanks for watching, and I will talk with you later. Bye-bye.